Hello everyone, we are going to study how to add and subtract vectors today. We're going to follow two approaches. The first one is going to be a graphic approach. Okay? So that will allow us to see what the resultant, which is the word used when you add or subtract vectors, look like. We're not going to get the coordinates or components of the vector at this point. We're just going to see what it looks like to develop an intuitive feel for a lot of things dealing with vectors. Okay, so let's have a little example right here. Imagine that you have a vector like this. Let's call it the vector u. So what matters when you look at a vector like this is to know its starting point and its end point. Okay, so this magnitude of the vector represents something that can be measured in meters per second, in Newton, in pounds, in whatever. But the magnitude or length of the vector is associated to a number usually. And the direction of the vector is traditionally measured like you would in trigonometry from the x-axis. Okay, so we have a starting point right here and we have an end point right here. If I take another vector, let's take the vector v for example. This vector v also has a starting point and an end point. Okay? So if I want to find the resultant of the vector u plus the vector v, which we can call w, the process is a purely graphical process. It's enough to move this vector such that the starting point of this vector is at the end point of the previous one. Because when you add vectors, you can also use the commutative property of addition. You could also move the starting point of the vector u onto the end point of the vector v. Let me demonstrate here. I'm going to take this vector v and I'm going to move it such that it starts right here. Now remember, the only thing that matters for vectors is the direction and magnitude. So I'm going to redraw this vector right here. So the length is approximately the same. It should be exactly the same, but this is something I'm drawing freehand, so not necessarily perfect. But the direction is pretty much the same, and the length of the vector, the magnitude, is pretty much the same. Okay, this will be the direction right here, and I've tried to keep it the same. So what will be the resultant? Well, you would start right here, you would end right here, and so that will be your vector W. What if I wanted to do now not u plus v, but u minus v? Let's pretend we have the vector u, we subtract the vector v from it, and let's call it something else. Let's call it the vector k, for example. Well, I will start again with my vector u, the same vector as before. And instead of the vector v right here, I will need the vector minus v. Because I can rewrite this as u plus negative v equal k. So what is the relationship between v and negative v? Simple. Same magnitude, but the exact opposite direction. So this here will be the vector negative v. So at this point, I just take this vector negative v, place it right here. That's a vector negative v. And so when I connect the starting point of the vector u to the end point of the vector negative v, this resultant vector will be the vector k. Okay? So graphically, that's really all you have to do. Of course, in most applications, what you want is to find the components of the vectors. And so when you want to find the components of the vector, you want to approach the problem algebraically. Okay? So let's pretend that we have a vector u again right here. And let's say that the magnitude of the vector u is 10 newtons. Let's also pretend that the angle alpha right here is 45 degrees. Okay? We can have it in radians as pi over 4, but I'm going to leave it in degrees. And then we have a vector v. Let's say that the magnitude of the vector v is, let's say 8 newtons, slightly smaller, and that the angle, again from the horizontal right here, let's call it beta, that the angle beta is negative 60 degrees. Okay? If you have an issue with the negative 60 degrees, just pretend it's positive 60 degrees. It's fine. So what do we do now to find the vector w and its component if the vector w is equal to the vector u plus the vector v? Well, what's interesting about vectors is that this one equation right here can be transformed into two equations involving components if you're dealing with two-dimensional problems, or three equations. Let me write those equations. We can say that the x-coordinate or x-component of the vector w will be the x-component of the vector u plus the x-component of the vector v. And the y-component of the vector w will be the y-component of the vector u plus the y-component of the vector v. Okay? Which means that from here, all we need are the components of the vector u. If you recall, the components of the vector u is going to be right here, u times cosine alpha, and right here, u times sine alpha. So 10 times cosine 45 should be about 7.1 Newton, and right here should be 7.1 Newton as well. Use a calculator if you want. 10 times cosine 45. I round it up right here, but it's the point here is to illustrate the approach. Okay? Let's do the same thing for the vector v. The vector v is going to be u times cosine, 8, times cosine beta, and 8 times sine beta. Again, you can have a calculator if you want, but 8 times cosine 60 is going to be equal to 4 times root 3. Now, I understand that if you write those values right here in decimals, you might want to write this right here as decimal as well. And I apologize for this. That's going to be 2 right here. Okay. And right here, 4 times sine 60 will be 4 root 3, which will be the 3.4 or 3.46 if you prefer. Okay. But let's look at the picture for a second. You see that the vector v is going to the right, which means that its x component will be positive. It's going down, which means that its y component will be negative. Now, if you had used negative 60 directly, it would have given you this directly. Okay. So if now we do this here, right here you're going to have 9.1, and right here you're going to have 3.63. Those are the components of the vector w. So let's write the answer. The vector w has 4 components, 9.1, and 3.63. We can do one more thing when we deal with vectors like this. So we have W, which has for component 3.63 and 9.1. And the question would be, what would be the magnitude of the vector W? And what would be its direction? Let's call it the angle theta. Okay, so let's draw the picture, or a picture that illustrates this. If we have a starting point right here, we're going to go 9.1 in this direction, because it's positive, and 3.63 in this direction, because it's positive, which gives us the vector W like this. Okay. So how do we find the components, the magnitude of the vector W? Well, this is just a right triangle, so we can use the Pythagorean theorem, telling us that this is going to be the square root of its x component square plus its y component square. So calculator time, 9.1 square plus 3.63 square equal, and we're going to take the square root of this, giving us 9.8. So it will be 9.8 Newton. As for the direction, if we call this again the angle theta, then we can say that tangent of theta is equal to 3.63 over 9.1, which means that theta is equal to arctangent of 3.63 over 9.1. So let's do that. Arctangent of 3.63 over 9.1. And we get an angle equal to 21.74 degrees. So the magnitude of the vector W is 9.8 Newton, and its direction is 21.74 degrees. I hope it was helpful.